Hello everyone, Mr. Linder here. Let's talk about properties of the respiratory system. So one of the first things we want to look at with the respiratory system is compliance. Compliance is the ability of the respiratory system to stretch. So in essence, we're talking about the ability of the lung to be able to inflate properly. Most of the work when we breathe goes into overcoming the resistance of the elasticity of the lungs. Your lungs and your thoracic cavity are trying to return to a resting position. So compliance is the ease at which we can stretch that tissue and therefore be able to inhale properly. Compliance refers to how much force must be exerted to change the overall structure of the respiratory system. And so it's expressed as delta V over delta P, which essentially implies the change of volume resulting from a given pressure exerted on the lungs. High compliance means that the lung stretches easily. Low compliance would mean that the lung requires more force from the inspiratory muscles to be able to stretch it. Typically, human lungs have good compliance, oftentimes expressed as hundreds of times better than a balloon. So if you've ever tried to blow a balloon up, you understand the concept of compliance. Some balloons will blow up easier than others. Well, our lungs should have high compliance, so therefore they inflate or they blow up very easily. Another property of our lungs is elasticity. Our lungs have elastic recoil, and it's basically the ability for our lungs to return to an original shape after that shape has been changed due to some force. Elasticity is actually a very important property when we talk about exhalation. Normally, when we inhale, right, that is a active process. We talk about it being active because it requires muscle contraction. But when we exhale, we talk about it being a passive process where the elasticity of the lungs, based on the elastin proteins that are in the lungs, they're able to return to their original shape, and thus we can exhale air from the respiratory system without muscle contraction. We simply can relax the diaphragm and air can flow out of the respiratory system. So active muscle contraction on the inhale, passive relaxation on the exhale due to the elasticity of the lungs. So if we're talking about normal function of the lungs, then we want high compliance. Right? We want to talk about high compliance or the stretchability of the lungs. And we also want high elasticity. We want the lungs to return to their original shape as easily as possible. So from a clinical standpoint, we could look at conditions that affect some of these properties of our lungs. The first thing we can look at is the idea of obstructive disorders. Typically, we refer to these things as COPDs or chronic obstructive pulmonary diseases. Chronic obstructive pulmonary diseases would be things like emphysema. And so what's happening in these conditions is we see increased compliance. We actually see the stretchability of the lungs go up, and that's because the elastin fibers within the lungs are being destroyed. And so the lungs have high compliance. They fill real easily. But without those elastic proteins, they begin to lose their elasticity. So we see increased compliance and we see decreased elasticity. And so what happens in those conditions? It's easy to get air into the lungs, but then it's harder to get the air out. Okay, so it's easy to get air into the lungs, harder to get air out. And so what we see happening is we see air trapping taking place. So when you think about COPD, we want to think about air trapping. When you trap air in the respiratory system, when you're trapping air within the lungs, it's going to become much more difficult to get fresh air back in, and therefore it's going to be more difficult to oxygenate the cardiovascular system because we're trapping air within the lungs. So that's chronic obstructive pulmonary diseases where you see increased compliance and decreased elasticity. Contrast that with restrictive disorders. In restrictive disorders, we see decreased compliance. We actually see a buildup of fibrous tissue within the lungs. Essentially, the lungs are developing scar tissue. And this could be caused by exposure to asbestos. This could be what's commonly referred to as coal miners' lungs, so exposure to coal dust, silicone exposure, any sort of environmental particulates that can actually cause pulmonary fibrosis to take place. And when that happens, your lungs actually become less compliant. It's a lot harder to inflate the lungs if they're resisting that expansion. So decreased lung compliance is going to make it difficult to inhale. So we're going to see a decreased inhalation. And decreased inhalation means decreased vital capacity. And so when your vital capacity is going down, that's the total amount of exchangeable air is decreasing. Again, we're having trouble oxygenating our cardiovascular system. So two different types of disorders, but ultimately we're affecting the ability to properly oxygenate the cardiovascular system and have proper aerobic metabolism within the body. Another property to consider about the respiratory system has to do with surface tension. When we talk about surface tension, we're talking about something called the law of Laplace. And the law of Laplace looks at the pressure related to surface tension. So 2T is talking about the surface tension divided by the radius. So P equals 2T divided by R. And if we were to apply the law of Laplace to two bubbles, so here we have a large bubble and a smaller bubble. Here we have a radius of 2 for the larger bubble, and here we have a radius of 1 for the smaller bubble. We have equal surface tension within the two bubbles, and so therefore if we were to calculate out the overall pressure within each bubble, we would see that the pressure within the larger bubble is less than the pressure in the small bubble. And so what we're saying is that inside, right, two bubbles of different sizes, the smaller bubbles will have more pressure within them. So if you were comparing this in terms of alveoli, so if you were comparing a small alveolus to a large alveolus, the air sacs that exchange respiratory gases of equal tension, the pressure within a smaller alveolus would be greater, and therefore it would take more work to expand that smaller alveolus. So if you're looking at your air sacs, if these are the alveoli, smaller alveoli, the small ones, are going to be harder to inflate. And so it's more difficult to inflate the smaller alveoli because in essence there's greater pressure due to the smaller size. So something needs to change in terms of the surface tension so that it's not as difficult for your respiratory system to inflate those small alveoli. So what our respiratory system does is it actually creates a secretion known as surfactant so that we can reduce the surface tension within the smaller alveoli so that they'll actually inflate just like a larger alveolus. So in this scenario, if we introduce surfactant into the system, so here we have the large alveolus, and here we have the small alveolus. Again, large bubble, small bubble. Radius of 2 for the larger one, radius of 1 for the smaller one. But notice what's different. The surface tension for the larger is 2. The surface tension for the smaller one is 1. So what's reducing? Why is the surface tension less? What's reducing the surface tension? Well, in our lungs, in the alveoli, we have something known as type 2 alveolar cells. And type 2 alveolar cells produce surfactant, which reduces the surface tension in the alveoli. So surfactant is decreasing the overall surface tension in these smaller alveoli. So how does that work? Well, what surfactant is it's a protein and phospholipid secretion that actually interferes with water's ability to hydrogen bond. So if you have water molecules in close proximity to each other, water molecules, because of their polarity, so positive on the hydrogens, negative on the oxygens, because of their polarity, the hydrogens will interact with the oxygen from both water molecules, and it actually draws the water molecules towards each other. And so this is what creates surface tension. So surface tension is created by the interaction between two water molecules because they're able to hydrogen bond with each other. So what the surfactant secretion does is it interferes with those hydrogen bonds. So again, if we have two water molecules in close proximity to each other, but you have surfactant secreted, that surfactant, I'll just put a big S here, that surfactant is going to prevent the hydrogen bonding between those water molecules, and so it's going to reduce the overall surface tension in that space. So as the alveolus gets smaller and as the water molecules get closer together, the surfactant that's in the space is able to keep those water molecules away from each other, thus reducing the overall surface tension. And so now if we look at the law of Laplace and run the calculation, we see that the pressure in the large alveolus is the same as the pressure in the smaller alveolus. But that is only going to happen if you're creating surfactant and it's reducing the overall surface tension. So another property of our respiratory system, a property of our lungs, is to produce surfactant for normal function to reduce overall surface tension. From a clinical standpoint, if you were to have newborn respiratory distress syndrome, we're talking respiratory distress syndrome, in premature babies, so we're talking about newborns, in premature newborns, premature infants, the lungs are less developed. And so if your lungs are less developed, you're not producing the surfactant necessary to reduce the surface tension within the lungs. So you're going to see difficulty breathing because it's harder to inflate those small, tiny alveoli. So what medical professionals can do is we can introduce an aerosol version of an artificial surfactant to help reduce surface tension. We can provide supplemental oxygen. We can provide artificial ventilation, so breathing for the infants on ventilators. We can also provide corticosteroids to help develop the lungs at a faster pace to give these newborn infants that are in respiratory distress a fighting chance at survival. But introducing that surfactant is going to be a key feature in helping those tiny lungs function properly. Another thing to consider when we're talking about characteristics of the lungs is looking at overall airway resistance within the lungs. And so airway resistance brings us back to the concept of airflow. So airflow is equal to delta P pi r to the fourth over 8L eta. So again, this is looking at Poiseuille's law, which actually describes blood flow in the cardiovascular system and airflow within the respiratory system. They each follow the same physics properties. When you look at the factors, changes in pressure, so that's ventilation. Length of tubing should be constant and not a factor when we're describing airway resistance. Viscosity of air should also be relatively constant if we humidify properly and if we aren't overproducing mucus within the respiratory system, then the viscosity throughout the respiratory system should remain fairly constant. And so that really leaves us with the radius. And so radius of the tubing becomes the main factor for talking about airway resistance. So compliance, elasticity, surface tension, and then airway resistance. So length of tubing stays relatively constant, viscosity stays relatively constant, and so that leaves radius of the tubing to be the main factor for affecting airway resistance. It's about 90% of airway resistance is typically in spaces like the trachea and the bronchi, which their diameters don't change typically, and that's because of bone and cartilage keeping those structures open. And so we have to focus then on the bronchial tubing as a means of talking about airway resistance. So the bronchioles are going to affect airway resistance if you have bronchoconstriction or bronchodilation. Bronchoconstriction is going to make the bronchial tube smaller, and so that's going to increase your overall resistance. So that's bronchoconstriction increases airway resistance. So we'll put airway resistance. If you have bronchodilation, you're going to decrease your airway resistance. It's going to be easier for air to flow through the passageways if they're dilated. So what are some things that are bronchoconstrictors? So one of the most powerful bronchoconstrictors is going to be histamine. Histamine is a powerful bronchoconstrictor that comes from mast cells, and this is going to be typically in response to things like allergies and or tissue damage that's taken place. Your bronchodilators are going to be things like epinephrine, epinephrine binding to beta 2 type receptors, and then carbon dioxide levels. Elevated carbon dioxide will give us bronchodilation. So increased CO2 leads to bronchodilation. Decreased carbon dioxide levels is going to lead to constriction. And so this is going to affect how we move respiratory gases through the respiratory system. The last thing to consider then is our efficiency of breathing. So if we want to measure, based on the properties that we've just looked at, and we want to measure how efficient the respiratory system is based on how well our lungs are being compliant, how much elasticity there is, what kind of surface tension there is, what kind of airway resistance there is. If we want to look at the effectiveness of ventilation, then we can calculate it by estimating how much air moves in and out of the lungs each minute. So one way to calculate the efficiency of the respiratory system is to calculate what's called the total pulmonary ventilation. Another name for that is the minute ventilation. So minute ventilation, it looks at our efficiency of moving air through the respiratory system. So how would we calculate that? So let's look at an example. In order to calculate your minute volume or your minute ventilation, we need to know the ventilation rate and we need to know the tidal volume. So your ventilation rate would be, for example, 12 breaths per minute. And your tidal volume is the amount of air that goes in and out of the respiratory system during a normal breath. So approximately 500 milliliters per breath. So if you're breathing at 12 breaths per minute and your tidal volume is 500 milliliters per breath, then your minute volume or your total pulmonary ventilation is about 6,000 milliliters per minute, which would work out to be 6 liters per minute. So your minute volume is approximately 6 liters per minute at 12 breaths per minute and a tidal volume of 500 mils per breath. Now, this represents the air moving in and out of the respiratory system every minute. But it's actually not a good indicator of how much fresh air actually reaches the alveoli. And the reason for that is that not all air is actually going to reach the alveoli because we're talking about a system of tubes that have to branch out to the alveoli. So if there's a tubing system that's branching out to the alveoli, then there's going to be air that gets trapped in the tubing. And the air that's left in the tubing and is not reaching the alveoli is air that's not actually going to be involved in ventilation. And so we refer to that tubing where air gets trapped as the dead space. So when you have a tidal volume of 500 mils per breath, not all of that 500 milliliters is actually going to reach your alveoli. There's going to be air that is trapped in the tubing. It's going to be lost in the dead space of the respiratory system. So if you're going to actually calculate efficiency of breathing, you would have to account for the dead space. So there's an alternative calculation that can be done, and that's known as alveolar ventilation. Alveolar ventilation is the ventilation rate, so how many breaths per minute, times the tidal volume, but we're going to subtract out the dead space to give us a more realistic look at how much air is actually reaching the alveoli. So what's a good estimate of dead space? Typically, dead space can be estimated at about 150 milliliters. Sometimes what we'll do is we'll estimate dead space based off of how much a particular patient weighs. So if you were to weigh, say, 100 pounds, then you might estimate the dead space at about 100 milliliters rather than using the 150. But for standard calculations, we'll just stick with 150 for now, and then you could use different estimates for dead space to get a slightly different number for future calculations. So let's take a look at an example. To calculate alveolar ventilation, which actually now is going to look at how much air actually reaches the alveoli each minute, we still have our 12 breaths per minute times our 500 milliliters, which is our tidal volume number. But now we're subtracting out the 150 milliliters per breath, which is the dead space volume. So what we really have is we have 12 breaths per minute times 350 milliliters per breath. And so that's going to give us a final number of 4,200 milliliters per minute, or 4.2 liters per minute, which is quite a bit less than the 6 liters per minute we got with the total pulmonary ventilation or minute volume, because that calculation did not account for the dead space. So 4.2 liters per minute is a more accurate representation of breathing efficiency, because we're actually looking at alveolar ventilation and how much air gets into the alveoli for gas exchange. So that's a little bit on characteristics of the respiratory system. I hope that helps. Take care.